Hello everyone, good evening and welcome to the November evening lecture organised by the IET Central London Network. I'm Rimesh Patel, a volunteer for the IET Central London Network, and I'm your host for today. We also have Matthew Davies, who's going to be our co-host. For today's session, we have about 125 registrations, so thank you all for registering and being available. At the IET Central London Network, we're a group of engineers that organise events that promote the IET's values, which are to inform, inspire and influence, just like today's session, which is on drone technology. I'm going to hand over to our speakers for today, Peter Katov, a development manager at Skanska, and John McKenna, the CEO of sees.ai. Thank you.
Okay, good evening, everyone. As Rimesh introduced both of us, my name is Peter Cater. I'm a development manager for Skanska, and I've been in the industry for quite some time, about 15 years, and worked on lots of different jobs in the Midlands and in London, and now find myself on a job in Surrey, which is housing development, building 1,200 new homes. My journey with this is I was introduced to John a number of years ago, and what he was doing was very interesting, and I'll leave it for John to tell you how.
Super, thanks very much, Peter, and thank you, Rimesh. So maybe just move on a slide there, Peter, if you could. I'm going to give about a 15-minute or so overview of sees.ai. Who we are, what we're up to, the sort of problems we're hoping to be able to address. I'll keep it deliberately quite high level. It's actually quite a technical subject on many levels between the actual technology itself and regulation, etc. So there's plenty of detail, and I'll not go into too much of that, but hopefully that will leave some questions for you all to ask. So, Peter, on to the next slide. We founded sees.ai in 2017. I've actually been working in the drone industry since about 2012. My first project ever with drones was working with a business called McKenna, which was part of Google X, or Alphabet as it's called now. And that business was flying large tethered aircraft to generate wind energy from high altitude wind. From there, I went to a business where we built drone swarms that could fly in the sky and do all sorts of pretty things for exhibitions and outdoor displays, etc. What I thought quite interesting during that time was that we were really at the very beginning of a new transition of technology, whereby we're starting to unlock a new mode of transport, let's call it, or a new infrastructure, which would essentially match road and rail and work very complementary with road, rail, and sea, and would really fundamentally change our lives. It will change, unmanned aviation will democratize airspace. We will all have access to aircraft, and an aircraft will be a part of our lives in a way that they absolutely are not today. We all get in cars every day, but we don't all get in aircraft every day or use aircraft. That will really change, and we'll look back at this point in time as a really interesting transition. Unmanned aircraft will change how we go to work, how we holiday, how we look after our infrastructure, how we inspect, monitor and maintain, and how we look after our world. So really, it's a little bit like the introduction of electricity or the internet or the mobile phone. We're at the very beginning, and we really have I deliberately use this rather large, strange looking aircraft because we really have no idea where this is all going to end up. We're very much at the beginning. Next slide. Let's say the unmanned commercial industry has been running for about 10 to 15 years. 15 years ago, hobbyists started to take mobile phone hardware, so very small hardware with miniaturized sensors and miniaturized batteries, etc., put propellers on them and realized that they could fly them. That early days, it was pretty exciting, but gravity is a hard taskmaster, and so those aircraft fell out of the sky a lot. And that was kind of the first problem. How do we build hardware that flies reliably despite the incessant force of gravity and all sorts of variables around movement of animals and wind, etc., in the air? And that problem was solved, let's say, in the first 5 years or so. The next problem that the industry addressed was when you fly a drone, you pull down an enormous amount of data. Most commonly, that's visual data, so cameras and video, but it can be radiation sensors or methane sensors or, hazard sensors. It can be a lot of different sensors, but generally they all generate a lot of data. And for big businesses that were used to doing inspections with clipboards, this was really a big journey to go from the practical, hands-on approach to inspection and monitoring through to a digitized world. That's taken everyone in the industry, whether it's end clients or suppliers, time to understand how to build the tools and use the tools and make them part of our everyday kind of workflow. So problem one solved with hardware, problem two solved with data analytics, particularly leaning on machine learning algorithms. The third problem is how to fly these systems at scale. And that, next slide, Peter. That's really the business. That's the reason we created sees.ai. Like many novel technologies, when they're initially introduced into our society, the regulators put down quite draconian rules. We have a rule which is pretty much standard across the entire industry called visual line of sight, and that requires a commercially trained pilot to be physically present on site with their drone and flying the drone, keeping it within visual line of sight, so direct, unaided line of sight. It means you can't fly behind a wall, even if it's only 10 feet away. And so that rule has been the standard rule, which we have developed the industry over the last 10 years. A great fit for purpose start point, but equally extremely difficult to scale. It means every drone has to have a pilot associated with it. It means if you build a large drone team, you have to have a large geographically dispersed team of pilots. That introduces variability, that introduces cost, it introduces risk. Of course, going on to industrial sites when you're not familiar with that environment is a time-intensive, expensive, and risky exercise. So fit for purpose for the start, but actually not a scalable approach. Next slide. So when we created Sees in 2017, I guess rather naively back then, I'd been flying and working with autonomous drone systems for quite a long time. And I, with a background in engineering, my original career was, I did an undergraduate degree in civil engineering, did a master's in Imperial College in structural steel. I worked in Arup, working on buildings like the new Grandstand and Lords, the Angel of the North, the new Houses of Parliament and Portcullis House. And I really saw firsthand, both on the design side and on site, the potential of aerial data to help increase efficiency, productivity, reduce safety, reduce carbon impact. Next slide. So we've been working on this now for 4 years or so. With a very strong team, which I'll talk about in a minute. We've developed what is now one of the most, if not the most advanced technology for unmanned flight. I've not seen anything that does quite as much as this. It's a system which carries essentially the same sensors as an autonomous car. It maps its environment in real time in 3D. It flies autonomously in accordance with that map. It captures data efficiently in accordance with that map. And then it intelligently understands the bandwidth that's available back to the pilot. And so it streams a very helpful synchronized version of the 3D model back to the pilot, which gives the pilot radical transparency in terms of how the mission is playing out, but also radical control of the mission. And so it's a very tight teaming of man and machine. Next slide. Part of the problem is, of course, regulation, as I talked about early on. And so we've been on a journey with NATS originally way back in 2017, which is the business that runs UK airspace. And then the UK Civil Aviation Authority for the last couple of years, working inside the regulatory sandbox, which is an invite-only group of entities working closely with the Aviation Authority to help them figure out how to do beyond visual line of sight as a matter of course, to help them develop the rules. So we sit in that sandbox alongside Amazon, Boeing, Volocopter, NATS, and a few other businesses in a fairly privileged sort of one-to-one communication with the regulator to define how this beyond visual line of sight might happen. And in April of this year, we were given one of the most advanced permissions in the UK to fly beyond visual line of sight. And in particular, what's advanced about it is it allows us to fly routinely beyond visual line of sight in non-segregated airspace. whereas previously most permissions were very specific one-off permissions in segregated airspace. So it's quite a step forward. Of course, there are constraints that come with that. The particular constraints that apply in our case are we fly in specific industrial sites and we fly below 150 feet. I'll talk a little bit more about that in the future. Next slide. What's made this possible is a strong core team. My co-founders have been working in Apple and McLaren and hedge funds and America's Cup. Between them, they've won one Formula One World Championship. So Richard was the voice in the ear of Lewis Hamilton when he won his first World Championships. Designed engines and gearboxes and supercars. Eduardo prototyped Face ID, led the team that prototyped Face ID at Apple, won 2 America's Cups with Oracle Racing, in charge of electronics and controls. Damien spent 15 years in hedge funds, simulating and then deploying code into the financial markets with billions of pounds of capital at risk. And then from there went into the British America's Cup team, where he led the simulation effort, the design of their hydrofoiling 50-knot race boat. So this is a pretty rare team that's gone from cutting edge innovation, the sort of innovation that wins you world championships in technology, right the way through to deployment. So volume deployment, whether it's in cars or boats or in capital markets. Next slide. Next slide, Peter. We haven't done this on our own, of course. Innovation in aviation happens very much in a coordinated way with all of the big players in the industry, ranging from NATS, as I said, that runs UK airspace, through to Vodafone and BT that provide critical infrastructure like the cellular network to make this possible. Hyperlocal weather, hyperlocal risk. There's lots of factors that are important we consider. Next slide. In particular, the thing that's different about what we do is the military have been flying beyond visual line of sight for a long time, 30 years or so. And so I often get asked what we're doing that's different or than that. And the big difference is when you're flying a military aircraft, you're typically flying far away from things. You're flying a very expensive aircraft at high altitude and using very powerful cameras to get the information you need. Our problem is different. We want to fly in industrial environments and we want to get component by component information. So to be able to look, for example, underneath an oil rig or at an insulator in a electricity grid. That means close quarter complex three-dimensional flight. And in order to do that and to do it in unknown environments, you need to build this very advanced autonomous capability. Next slide. One of the interesting outputs of this 3D modeling approach is that simultaneously the system maps its world in 3D and takes images. So we're able to map the 2D imagery into the 3D model. So we actually delivered structured data. So if you typically fly a drone, you have 1,000 images you capture, and machine learning algorithms can spot a problem, but you don't quite know where the problem is. With this approach, the geo-tagged or geo-locked 2D images in 3D model mean in any 2D image, if your machine learning algorithm spots a problem, you can locate that on the 3D model. That's super helpful. Next slide. This whole architecture has been designed to scale. So we built it on the cloud so we can deploy it at large scale. Any number of systems can be flown by any number of pilots located almost anywhere. Latency isn't particularly a problem because the system is flying itself. And it's connected and autonomous. So the system ultimately takes care of all low-level control while the pilot is involved in the mission, setting the high-level task, and from a regulatory point of view is an important contributor to safety. Next slide. One of the interesting things about this particular approach is that because when every system flies, it's cloud connected, we ingest a huge amount of data from every flight, and we can use that data to improve how the system performs and to prove and capture data about safe flight as we progress. So we're able to demonstrate to regulators, procurement professionals, insurers, customers, and clients that the system is safe and fit for purpose before we advance to more complicated missions. We're leveraging quite advanced tools, as you would imagine, from Formula One and hedge fund days, analytics and diagnostics, a lot of simulation to make sure that before we ever fly a system for real, we've tested it in simulation. So the whole architecture is deploying a lot of software to make sure that we extract maximum value from each real flight that we actually undertake. Next slide. Our start point is unusual or different to most. Next slide. So many drone businesses have started by flying in rural or remote locations or in poorly regulated spaces in order to first build safe flying hours and then to be able to prove their safety or demonstrate their safety to regulators. We've got a slightly different approach in that we believe if you're going to sack Troy or win Troy, you're better off starting on the inside of the wall. So next slide. Yeah, so we've been working with a large number of asset owners and operators to help them understand the potential of our system, but probably more importantly for us to more deeply understand their problems and to find out where our technology can be best used. Next slide. Over to you, Peter.
Okay, brilliant. Thank you, John. So I suppose that's cool. And the big question is, okay, so why does that matter? Why does that matter to the construction industry? And when I first met John and he explained what he was trying to achieve, why should I pay attention? Before we move on to answering that question, I'll be using the term drone, and I know it's used in the strapline of the title for this presentation. For those of you who are buffs out there and are going to call this up on it, we know that it's UAV, which is unmanned aerial vehicle, but people are more comfortable with the term drone. So we'll be using it throughout. So why does it matter to us? Why does it matter to the construction industry? Well, we build big, cool, tall, complex things, and by their very nature, we have a requirement to view them, to check them, to survey them, to manage them, usually from height. That's the challenge that we're trying to solve. But we do have traditional methods, and it won't be. I'm sure the engineers out there are not unfamiliar with scaffolds and alley towers and cherry pickers and broad working at height. But all of those things, they have to have a level of skilled operatives. Those skilled operatives have to travel to site. They usually have to travel to site with the specialist equipment. They all incur cost, and they all generate carbon, and it all places people at height. Or, as we so often do, we just don't check. So if we don't meet that first obligation of cost, so often the parts that we want to check or we'd like to have a look at just don't get done. So leading on to drones as we know them in the construction industry, and you may or may not be familiar with this. So current drone use in the amateur sphere, we have seen this on sites. People who've bought one for Christmas, or they're just an enthusiastic amateur, even if they've got the appropriate licenses. It presents issues for us on site for as far as risk assessments are concerned, for their insurance, public liability insurance, the legal aspect of requiring certain permits and then permissions. So permission is required to fly over anyone else's property. Quite often the accuracy and the resolution, and that leads on to the reliance. So generating reports either by camera or video, and then having an element of reliance in that. So a company that you can go back to and say, you know, is this what we're seeing on this day, and in this detail? And broadly, they are camera only. It says at the top there GDPR. If you're not aware, if you have a camera or a video and you're taking shots even on your phone, there are GDPR issues as far as getting consent, written consent, and all of these things are generally overlooked. It's not uncommon for people to, and you may news, people complaining about videos flying over their back gardens. You have the same issue on large construction sites where you're not appropriately blanking third-party properties or third-party neighbours. That kind of information then could look nice, so it goes to publish, and you can be hit with fines. And then we also have current drone use, which is professional. So broadly, they're legal, insured, and reliant. There's multiple payload options, so there's not just the option of having camera and video. You do photogrammetry, you can do LiDAR, you can do heat signature, multiple different payloads. Generally, a two-person operation in order to get the insurance. So in order to get the insurance and to complete the RAMs, certainly for the larger sites, is a two-person operation. It is not inexpensive. This is not the point where I'm going to say it's prohibitively expensive, and to some of the traditional methods it can be comparable. However, it is not inexpensive. And there is low industry take-up. Low industry take-up because of bad experience previously. So as John was saying, this technology has been in the go for a number of years, and like the internet bubble, there was a lot of people straight away going, I can do drones, I can do drone images, but they were many thousands of pounds, and the data would take quite a while for it to be processed and then returned to you, and perhaps it wasn't really what you were after. So low industry take-up because there's some bad previous experience. There's certainly poor understanding of what can actually be achieved through use of professional drone companies, and knowledge of the payload and the accuracy that can be sought. And we generally are not, because we're not furnished with those details, we're not good at presenting and making those cases. We're not good at saying, okay, here's the cost of an alley tower with the 2 men for the 3 days, and here is the cost of a professional drone company. So we're not good at it. But both of those options, whether it be amateur or professional, they both require line of sight, so direct line of sight, visual line of sight. So as John said earlier, that is the operator, the pilot, being able to see the drone at all times. And as John was saying, what we're looking to do with this technology is take it beyond visual line of sight. So beyond visual line of sight, or BV loss, catchy little phrase, BV loss benefits. In essence, there are no people required to attend site. BV loss is perfected. There is no requirement for people to attend site. If there's no people attending site, there's not the 1 van, the 2 people, the cost incurred of that, but certainly no carbon from that. And because there's no people attending site, there's less risk, okay? And less carbon, less risk, less people does lead to less cost. Now, as we know with many things, that when we lower the cost of delivering a solution at speed and at quality, the solution then becomes ubiquitous. So imagine Amazon, if someone had told us 15 years ago that there would be free next day delivery on almost any product you can think of, it would be mind-blowing. Today, we're at that point. We're at the point where we're paying delivery every time, and we're saying, well, I don't think I should get it delivered. I'll go to the shop because delivery is costing so much. So this picture here describes BV loss in its infancy. So there's a lot more work to do, and there's a lot of regulation to get through, and a lot more technology to evolve. But certainly, this will change the way we work and live. Absolutely, and there will be benefits that we cannot even begin to realize or visualize at the moment. But I believe, looking at this picture, that we're in a period of our history where we'll look at photos like this with the same disbelief as we look back at images like this. The image we're looking at now it's obviously not a photograph. It's to describe the 1865 Red Flag Act. So to describe the 1865 Red Flag Act, the locomotive engine powered by steam was seen to be such a risky and threatful and fast piece of machinery. You see a horse being scared in the background and a policeman waving it past. It was deemed to be so risky that it was law that you had to employ a man to walk no less than 60 feet or 60 yards in front of your carriage carrying a red flag. The maximum speed of these vehicles was 5 to 6 miles per hour. If we imagine this image here and what we now know as our automotive industry, our transport industry, and every area that the development of this particular image and the genesis of this particular image is taken, that is where we are today with drones. What you're about to see is a video shot at our development in Mindenhurst in Surrey. This was the first UK test of BV loss technology with Sees and John. Very proud of the results. And what you'll see as it comes up will be an operator, the pilot, who sat 50 odd miles away. He's the one operating the drone. You will notice there's footage taken from the air of that drone. So yes, there was another one in the air, okay? While you watch this, just think about the possibilities. Think about if you had a drone in a box on your site and you could press a button and scan anything for almost zero cost, what would you look at? Mm-hmm. Okay, thank you.
Great, thanks very much, Peter and John, for an excellent presentation. There's been quite a few questions coming in. They're sort of broken down into two separate groups. Those that are more interested in the drone technology itself, and those that are interested in the application of it. So if there's quite a few on the drone tech itself. Obviously one of the big questions is around how reactive the drone is to considerations such as changing weather conditions, in particular with the applications presented here, to gusts bouncing off the structure, and things such as the flight time of the drone. Is battery a barrier to long flight times that may be necessary for the applications that sees.ai is looking at?
Do you want me to answer a couple of those questions?
Yeah, please.
Yeah. I realized just listening to Peter that there's one point that I made which is potentially misleading, and I should correct it. So the work that we've been doing in testing with customers over the last year is not with a final commercial product. So the tool that we're using is what we call an alpha drone, or an alpha stage system. So just the one stage before a commercial viable product, fully designed right down to cables and connectors. So if anything goes wrong, we can fix the design and build it. And so that's a single system, and it's been designed with an objective to cover a really wide range of use cases. So it's kind of jack of all trades, master of none. The next stage is when we are narrowing down to the 3 use cases I mentioned in the presentation. So that system will be much more custom designed to that. So I guess that's the overall picture, which is when I answer these questions, it's the answer that I'm giving you is for the system that we've currently designed. So in terms of reactivity, the software is not a constraint. So millisecond by millisecond, it's positioning itself relative to the world that it finds itself in. So the software bit isn't a problem. The hardware reactivity is down to a number of different things. The configuration and the number of blades. So a helicopter is not a particularly maneuverable tool, whereas a multicopter is. And the more engines on board, the better. And the power, of course, to be able to actually hold on to the air. But from a computing point of view, the system is holding itself to within a couple of centimeters. In reality today, in sub 20 knots, our current drone system will hold itself in about a foot diameter circle. As it gets windier, of course, that system won't be able to resist the wind forever. It's deliberately, we're not really addressing high wind scenarios today. The team has a huge amount of experience in control and dynamics, but we haven't tried to address the extreme case where we might fly it on an extremely windy day. So the practical realities we put in place are, we don't fly it when it's extremely windy today. So in theory, it isn't going to be a problem to deal with weather. In practice, we've made some constrained choices today. In terms of flight time, the same question really applies. So it's kind of the reverse. So helicopters are extremely efficient, whereas multicopters are extremely inefficient. We've chosen to use an oct, so it's an inline oct, so it's effectively the quad orientation, but 2 blades, one below the other. It's quite a compact shape, but it's not hugely efficient. At present, that drone can fly for about 30-35 minutes in theory, but we typically stop with about 30% power left. But again, when you're optimizing to address a particular mission, for example, we are now optimizing to be able to fly for 2 hours, you'll choose a very different configuration and a very different powertrain. We're certainly exploring chemical fuel powered drones as well as battery. Yeah, so some clear design choices made on what we have today.
That's fascinating. And I mean, obviously there's other considerations around communication and
Yeah.
recovery of drones if something does happen. So what sort of, there's a question from Salah or a couple of questions from Salah Al-Chalabi about the network infrastructure that's used, reliability, interference.
Yep.
And then how would you recover a drone if it was lost because of some failure in that?
Yeah. Well, so we use the cellular. We use whatever comes as available, but to be honest, the existing powerful infrastructure that we have now is cellular infrastructure, and there's lots of different carriers, so it's helpful. We get approached a lot by businesses who are very excited about 5G, and of course, if we have 5G, and if it really is everywhere, then the problems fall by the wayside. But our real problem today is not 5G, but kind of no G. That's the reality of the UK still, and of many countries really, is that if we've 3G, we're happy. If we've 4G, we're delighted. We never have 5G. So the regulator has a couple of very obvious questions they ask day one. Day one question is, what happens when the system loses comms? And it absolutely will lose comms. That's part of the fact of life, even with just making a phone call these days. So the start point for our design was that the system is safely able to operate autonomously in an unknown environment. If it's GPS denied, comms denied, if compass has gone haywire, it still needs to be able to execute a safe return to home and a complex return to home doing dynamic collision avoidance and path planning. So even in a complex environment which is changing, the system will execute a safe return to home or a safe landing. It's up to the pilot to set some parameters as to how that execution would take place. It's a kind of a design decision depending on the nature of the flight you're executing and the environment you're in. But we use the cellular network primarily. When it works, cellular network is already a variable resource in terms of bandwidth and latency. The system does a lot of work on board to figure out what bandwidth does it have, and then to adapt the information that it's sharing with the pilot depending on that bandwidth. So if it has high bandwidth, it sends a high resolution model, or it synchronizes a high resolution model. So it's never sending information that it knows the pilot has already received. It's sending deltas. If you've got low resolution, it starts to send a much blockier world. So you see much more of a Minecraft world. Then it starts to do things like it sends you information that's closer to you before information that's further away, or information that's, a moving object is sent before a static object, or cables and trees and people. It's picking out things, and it's using its hierarchy information to send the most useful information to the pilot depending on the bandwidth that's available. But yes, we lose comms and we deal with autonomy, bandwidth variation, we deal with like that. Latency isn't really a problem because you're never on the sticks flying the drone like a sort of conventional drone pilot would be. You're issuing very high level instructions. Fly to a waypoint would be the most low level command you'd ever give. And the system executes its own dynamic path planning to get to that point. So if by mistake you've put a point in space which, if the drone flew from where it is now to that point, would cause a crash, the drone will do its dynamic path planning to get to that point. Mostly what happens is you've set up a much more complex mission and the drone is just playing it out and you're watching as a pilot. In terms of what happens if we lose a drone, that's just something we've got to deal with in the age-old way of going and getting the drone. there's nothing nothing more clever than that. Yeah, so that's something you've really got to avoid.
And if you're dealing with say flying objects, so aircraft, birds, how does the drone cope with those? Does it rely on aircraft having transponders, or does it observe movement of aerial objects? Do you need higher resolution cameras for that?
So it's a journey. So the regulator is quite rightly not in the business of taking risk. So part of the design of our business is, as I mentioned, when I was talking about Troy, our setup has always been to present a technology to the regulator that has the potential to go all the way to mobility. So it's solving all of the fundamental problems, but to put forward a safety case which is presenting a very, very low risk mission. So if we ask the regulator, can we fly down Oxford Street? They say no, of course. If we say, can we fly in an industrial facility where the public are excluded, where workers are wearing PPE, where workers are briefed, and where we're flying very close to the assets on that site, never far away from the site, then we present very low ground and air risk. So we're effectively putting ourselves in a place where really aircraft shouldn't be, and if aircraft are there, they have much more to worry about, and equally where general public shouldn't be. So that's the start point. We're sort of de-risking the mission in some quite practical ways. Being able to fly close to structures and metal structures and high voltage power line is extremely technically difficult, but from a risk point of view, it's quite good for the regulator. As we extend outside of industrial environments and into the public domain, there's more we need to do. So the drone doesn't sense it doesn't have powerful cameras on board to sense aircraft that are fast moving and far away. So there's other surveillance tools we need to put in place in the facility or in the surroundings to ensure that airspace is not being used by others. But it's, with everything in airspace, there's multiple tools and techniques you've got to use, technical and operational, to try to de-risk this situation. But in the drone that Peter showed, that's essentially doing detect and avoid of its surroundings, not versus other aircraft, because it's not flying in manned airspace typically.
Okay. And in terms of the applications, have you flown the drones remotely on structures such as offshore oil and gas facilities with no pilot on the facility?
No. So we are at the stage where we're flying an alpha system where we are deploying it in sites that are more controlled and less intense than an offshore oil rig. For us and for the customer, we need to go a little further down the path before that becomes a reality. It's a very interesting use case because it's incredibly expensive to fly a system on an offshore oil rig, but equally it'll be a journey to get there. We're not there yet.
And what sort of qualifications do the remote pilots need to pass as imposed by the CAA?
So standard commercial drone pilot license, and then extra training from us, which isn't particularly onerous. So they don't need to be a specially qualified pilot. Yeah.
Okay, no, that's fantastic. Most of the questions that I'm going to pass on now, I think it's sort of a toss-up whether it's for Peter or for you, so John. So yeah. I'll let the pair of you decide who's the best person. But if we jump into the use case that you've presented, Peter, so is a previous model of the site needed for BV loss, or is the whole point that it builds up the model from the ground up?
I think that's one for John.
So one of the fundamentals is that, let's say, the canonical problem we address is how do you fly safely when you have zero prior information and you have zero infrastructure supporting you apart from comms. So we build the model on the fly. We never fly versus a historical map. If we have a historical map, it can be helpful in terms of designing the mission, but you never fly in real time versus something that you assume is going to be there or not going to be there. You have to fly versus a live map.
Okay. And in terms of the carbon footprint, with the drone example that was used, obviously, I presume, given what you've said, John, that the drone would normally be flown to the site and then perform the scanning as part of a single operation. But was the drone delivered for that example and then flown as a demonstration, or Is this something that
if I
might
take that
happen?
one, John? Yeah, thank you, Matt. Yeah, as John said, we and probably, you know, I was trying to demonstrate, we are in the locomotive phase, and there's a guy with a red flag out front. But what we're doing is we're trialing it in certain areas without a guy with a red flag. Yeah, the vehicle still needs to get there. So on the example we gave in this trial scenario, yeah, we didn't cut any carbon. There was still 2 guys coming to site. The drone still came to site. But what I'm asking you to take the step with me is to say, if this was in a box, like a Roomba, you know, those the things that go around and hoover your houses and return to a docking station. If you had one of those on your large construction site, or you could ring someone and know that it could be flown from a central base and arrive at your site within 20 minutes, to get up at that high level detail to see if the steel fixers have done their job properly, or if it's if there's a dilapidation in an existing structure that you're trying to survey. If you had that and it was at low cost, that would be the obvious choice. There wouldn't be a second choice. You would not send men up an early tower. So does it cut carbon today? No. Will it? I think absolutely.
Okay. And is there a use case where you would see more than one drone being used on a single site? And if so, would each of those drones require a separate pilot, or would they be able to control, would a single pilot be able to control multiple drones effectively flying in concert?
I could answer that. I'm trying to remember what year it was. 2015 or 16 or 17, we flew 15 drones with 2 dancers all the way through to the semi-finals of Britain's Got Talent. Luckily not me as a dancer. So flying multiple drones in a swarm is you know, if everything's pre-coordinated or if you have central control, is easy. What's difficult is trying to get drones to truly fly in swarm, so to really coordinate with each other. That's not something we've spent a lot of time on. There are efficiencies to that, but it's extremely technically difficult, and the regulator, you know, at this point in time is not really thinking that far. We have to walk before we can run. And so because our system is a connected system, a cloud connected system, we are working right now to be able to fly, and working with the regulator to make this possible, to be able to fly 2 systems using a single pilot. So a technician would put a drone down and it would fly for 2 hours down the grid and back again with a single pilot. That's not possible today from a regulatory point of view. Technically, it's relatively straightforward to do if you have if they are connected systems. But like everything, in order to make that safe, there are lots of belt and braces. You have to put a lot of different mitigations in place to make it possible, not just intelligence on board the drone or intelligence in the cloud, but operational mitigations as well. So it will absolutely come, and it's of course why we started with autonomy first. The long-term vision is the system flies itself and has very little oversight from the human pilot, and so we will start with one pilot, one drone, a remote pilot and a drone on site, and we will evolve towards systems that only call in pilots whenever there's a problem. It's a journey. Just
to add to that, John, I think it's really interesting. The question starts with, can you see a use case for 2 drones at one time operated by the same pilot? Well, I suppose there's a question for you all to take home. This is a business where use case drives technology, and that's why John and I, when we talk about, okay, so how would you use this? What would be useful for you? And really, it's a challenge to you all to go away, and when you're next walking around your site or looking at your next project, just to think of, how would I use this if it was there, if it was just there and almost cheap, almost cost neutral. How would I use it? And if the answer is I would use 2 drones, then that's where that's where an option will come from. That's where it will come out.
Absolutely. Yeah.
I think that's the first time in any of the Q&A sessions where the challenges come back from the speakers to the members of the audience. So that's brilliant. Returning to issues specific to the drones, is there a risk that drones can be hacked?
Absolutely. Yep. Yep. A lot of work needs to be done to make that as difficult as possible. You know, Damien led a team deploying billions of pounds into capital markets. You know, everything's vulnerable. You just need to employ the right people and do the right work. Today, I would say the protections we have in place are, you know, adequate for the stage we're at, but there's a lot more work that we need to do, and we'll be working with external experts on that as well. It's a particularly, you know, specialist industry. Yeah, so that's
we
important. We deal with it.
Sorry, John. We are in a world now where everything can be hacked. Our cars will be electric. Our smart homes, everything that we interact with has the possibility. And as John said, it's about taking sensible precautions and putting the right security measures in place. So I don't, if there was a suggestion that drones being hacked is any more dangerous than an articulated lorry delivering goods to and from for Amazon, I'm not sure. That's a judgment that you'd have to make.
Yeah, no, I take your point. And if the drones were particularly large, then being around sensitive installations would be a point of issue. But for the size that we saw in that video, then it doesn't look like there's that sort of danger.
I would say on that as well, Matt, that interestingly, we are migrating to a world where technology such as proposed by Sees is and will be more trusted than the fallibility of the human. So when we're talking about the dynamic path analysis, this analysis, it doesn't get tired, it doesn't have lay-ins, it doesn't get sick, it processes through a system. So we find that actually it can be a lot less, or it could be more risk averse for sensitive installations.
And one thing to add to that, actually, it's a great point, Peter. So the code that we use on the drone today is deterministic. So we're not using deep learning algorithms in the control loop. And really it's, you know, related to this point. Today, the regulator wants to go on a journey that's predictable and you can improve. You know, our choice was to lean into that and build a system which we could debug if something went wrong. At some point, we'll increase the involvement of deep learning algorithms in the control loop. But you know, this is all steps you've got to take that you know, are guided by and allowed by regulators. So yeah, it's quite a, you know, crawl, walk, run approach.
And how do you see the industry evolving? Would tethered drones gain market share?
I mean, the tethered drone is fantastic for, you know, long endurance application, but it's probably not the right choice for beyond visual line of sight. The very long tether if I want to fly for 2 hours down the power line. But yeah, you know, I think there'll be lots of different solutions to power, and power for drones is a big constraint. So there's a lot of work being done in that area, and it's related to power trains. You know, it is a big problem that these drones don't fly for very long. Like a drone that flies for 3 hours is really an extreme, but equally a helicopter doesn't fly for 3 hours, you know. So, you know, I think we can approach what a helicopter does today, but to go further than that is Yeah, it's challenging. Luckily, we're leaning in many of these areas that we're, the technologies we're using. In fact, we're really following, in the original creation of a drone, that was following the work that was done in the telecoms industry with mobile phones. Now the heavy lifting is being done by autonomous car businesses. We're seeing sensor price and cost and weight reducing radically. So there's a lot of spin-offs from other industries that are very beneficial for the drone industry.
And in terms of a completely different use case, obviously drones have been used by the military for decades now.
Yep.
Is there an option for smaller drones to be used for security purposes? One of the examples that was posted in the Q&A was Network Rail using UAV patrols to combat copper theft and graffiti on rolling stock and depot boundaries.
Yeah, and there are some quite mature businesses now, Airbotics, Azure, Percepto, who have built a drone in a box with some relatively straightforward technology that uses GPS and comms to fly a simple box route over an industrial site. I'm not sure if it's legal here in the UK, but technically it's quite simple to do very high level overview of industrial sites. And so I think 100% that's going to be part of the tools, one tool of many tools that security firms will use alongside CCTV and manned patrol. But an eye in the sky is something, that gives you an extra advantage versus nefarious actors. The other question in the similar question was around piping industries and oil and gas. It's a slightly different use case. Security, typically you're quite remote, and you've got to, you really want to be able to cover a large area. When you're talking about piping and industrial assets, you want to get very close. That's much more kind of leaning into what we're focused on, which is how do you accurately image a three-dimensional object or fly around a three-dimensional object, such as an oil and gas asset or a chemical asset. Or even the construction sites we've been talking to Peter about. These are complex environments that you need to be able to fly complex paths inside, and you have all of the problems I talked about at the beginning of losing GPS, etc. So yeah, I think we'll see both systems designed for high-level overview and triage, and systems designed for really getting down into the three-dimensional world we all live in to get close quarter inspection very efficiently.
Well, thanks very much. That was absolutely fascinating, and the fact that we've managed to hold on to so many of the audience indicates that everybody really enjoyed it and loved the answers that you gave to the questions that were posted. So thank you very much, John and Peter, for your answers.
Pleasure. Absolute pleasure.
Ramesh.
Thank you, Rimesh. Thank you. Yeah.
All right. Yep. Just to echo that, Matt, thanks again, Peter and John, and thank you, Matt, for co-hosting. Now, before we conclude for today, please take a look at our December events. These are in-person events, and they're all in line with government guidelines. Our Xmas special is actually with the Science Museum, and as with all our Christmas events, children are welcome. So that should be a fun event because it's co-hosted with the Science Museum. We also have 2 Friday lunchtime events, and more details about them and the Christmas special can be found on the IET events website, as with all our other events as well. So please do make sure you attend our December events. And then for social media, you can use our social media channels to continue the conversation online. And we'll also be emailing you out a feedback form. So please do provide your feedback because it helps us design these events, and as well as it helps us provide feedback to the speakers. So once again, thank you all to attending today. Thank you to our speakers. Thank you, Matt, and have a good evening. Goodbye.